presented by Jim Schwarz, University of Syracuse.
I have three objectives in my presentation this morning. First is to introduce you to a concept that might prove, a design concept that might prove to be significant in developing a new class of metal-supported catalysts. And the second objective is to identify those elements of that design concept that needs to be put in place in order to make the concept viable, and demonstrate finally that, in fact, that the possibility of selective metal support exchange on composite oxides is possible. The work that I'll be talking about today was, portions of the work was supported by the Department of Energy, Basic Energy Sciences. Now, in catalyst design, it's well known that the performance of the dispersed catalytic metals is strongly dependent upon the carrier. And if we consider those systems in which we deal with exchange, or the driving force for a transfer of ions from solution to the oxide support is through electrostatic interactions, then there are two important considerations that we have to consider that must be made. First is that these concepts emerge from colloidal and interfacial science. The point of zero charge, the PZC, is an index of the exchange capacity for metal ion adsorption during catalyst preparation. And the initial rate and the adsorbed amount depend on the ion and the support. Now, I assert that composite oxides provide a suitable substrate for testing the hypothesis of selective metal support exchange, which dubbed the acronym SSMSD. Now, before I get to that concept of SSMSD, I'd like to just bring out some of the elements that are necessary in order to put that concept in place. And what I'd like to consider is a simplified surface ionization model in which I make the assumption that I have a single, simple amphoteric hydroxide site on my oxide surface, which can either be protonated or deprotonated, controlled by the dissociation constants K1 and K2. And that H plus and OH minus are the potentially determining ions in the system. Obviously, the extent of each of these reactions will depend upon the proton concentration and the magnitudes of K1 and K2. Now, if one has those values available for a system, and in addition has some information about the total number of amphoteric hydroxyl sites, one can generate a surface charge speciation diagram, which gives us how the positive and negative surface charge carriers, as well as the neutral charge carrier and the neutral carriers, vary as a function of the pH of the solution. Here in such a simulation, this is for a PZC of 5. The PZC is the point of zero charge. It's where the number of positive surface charge carriers and the number of negative surface charge carriers are equal. And we see for this particular simulation that the number of neutral carriers is quite large, percentage-wise. The DPK is another parameter of this surface ionization model, and that's just related, again, to combination, or is related to combinations of those dissociation constants, K1 and K2. Now, it turns out that the PZC is also related simply to those dissociation constants, K1 and K2. So we would like to have available, another element we'd like to have available, is a way of measuring simply the PZC of an oxide system. Well, we've observed in the laboratory that if we add incremental amounts of mass of solid, right, to water and measure the pH, doing it reasonably carefully, that there is a change in the pH of the solution, and that eventually, when we add enough mass content, that pH comes to an asymptotic value. We call this mass titration. And the observation is that the pH of an oxide water suspension changes in response to the amount of oxide added and reaches a pH value asymptotically. Now, I will demonstrate very quickly with my only mathematical slide that, in fact, that value of the pH corresponds very, is a good estimate of the PZC of the system. If one takes the equilibrium reactions that control the protonation and deprotonation, along with the electroneutrality condition, and then inverts that expression, one can solve for the total number of amphoteric hydroxyl sites, N sub T, in terms of all of the variables in the system. Now, without going into any details, the important consideration is what happens in the limit as NT, the number of amphoteric hydroxyl sites, goes to infinity. Well, in that limit, this denominator must become equal to 0, and in that case, the bulk hydrogen concentration is just given by the product of the two dissociation constants raised to the 1/2 power, or the pH of infinity, that is the pH where I see this asymptote just goes to the mean of the two pKs, which is by definition just the pH of the PZC. And N sub T is proportional to the mass content of the solution, is also proportional to, and N sub T is proportional to the mass content in the solution. So we now have available a simple way of measuring the PZC of the system. And let me look at three such systems. Let me look at pure alumina, pure titania, and then just a physical mixture of alumina and titanium. Now, there are several things to note about this slide. What I've plotted here is the pH versus the oxide content in mass percent. And what we observe is that, number one, in each case, there is an asymptotic value that is reached at high mass fractions. That, number two, the PZCs, you'll have to take my word for it, for the pure components, the alumina and the titania, are in reasonable agreement with the standard potentiometric titrations of those oxides. And we note that the physical mixture of alumina and titania is in fact intermediate between the two values for alumina and titanium. And in fact, if we make up a number of physical mixtures, and we look at the data for the PZC of each of those physical mixtures as a function of, we look at those values, we see that in fact, as seen up on the top here, that in every instance the physical mixture is intermediate between the two end members, the pure oxides in the system. And we sort of way to correlate that data, and the only way that that data correlates is based on the area that's exposed, right, to the aqueous phase, and that area is determined by the BET area of the two pure oxides. So when we make the physical mixture, it's the BET area, or the area of each of the oxides, which control the measured PZC of a physical mixture. Now, what our interest was in was not so much physical oxides, but composite oxides, because those are the systems that we'd like to test the concept of SMSE. So when we prepare composite oxides of titania on alumina, or alumina on titania by doping the pure supports with the appropriate isopropoxide, what we find is that, for example, in the case of titania on alumina, that as we increase the titania weight percent, that the PZC drops from that of pure alumina and is intermediate in the same way that the physical mixtures were between alumina and titanium. Well, using our previous knowledge of the behavior of the physical mixtures, we proposed that the PCC of the composite oxide is the surface area weighted average of the pure oxide PCCs, or, if you will, stated as a mathematical word equation, that the PCC observed is going to be related to, based on surface area weighting, the PCCs of the two pure components. Now, in this relationship, we measure the PCC here. We have the PCCs for the two pure supports, and we have the BET surface area of the substrate. And what we need is the surface area of the dopant. Well, the dopant surface area can be evaluated from a model. And the model we consider, and I'm looking at now titania on alumina, but it's equally as valid for alumina on titania. Small, highly dispersed crystallites of titania, occupying some area on the alumina surface, and we express the hypothesis mathematically, as I've done here, based on the geometry of the system. There are two unknowns in the system: the number of crystallites and their size. Well, we can get that information by the weight loading requirement, the formula or the relationship between the weight loading and the parameters of the model. And that gives us two equations and two unknowns, which can be solved simultaneously, and we can get values of n and d from the model. And furthermore, we can also calculate the percent area that's exposed by the dopant. Well, using that model, we take the data for the composite oxides, we make the calculations, and the thing to be noted from this very busy table is that, number one, that the size of the crystallites, that is the dopant, on the substrate, are very small. Now that's consistent at least with our X-ray results as well as the TEM results that emerged from the Exxon laboratories. And also that very small percentages of a dopant contribute a considerable amount of area, all right, this is the percent area, to the overall system. That's because they're highly dispersed. Well, now that at least brings me up to the point where I can tell you what SSMSD is. Now conceptually, since each of the oxide phases act, if you will, independently in the aqueous phase, then we can imagine a situation where by adjusting the pH of an impregnating solution to some particular pH star, that the surface of titania, for example, would be a good cation exchanger, whereas the surface of alumina, all right, would be a good anion exchanger. Now, using this as a concept is only part of the story. I think it was Paul Harvey that said something like that. Because then we also have to look at the aqueous phase. And that's an important consideration. We have to find a metallic precursor whose speciation we know at that particular pH star. Now it turns out cobalt is a nice suitable precursor. Now this is again a very busy diagram. The only one thing that I want to mention to you about here, this is a CT diagram. This just gives you these ions, the speciation as a function of pH. And the important thing to note is that the cobalt 2+, all right, is the major species, regardless of what the concentration in the solution is, at pHs less than about 8, say. All right, so our speciation is aqua cobalt 2+. Under these conditions, as long as the pH is low around 7.5 to 8. So now to demonstrate that SMSE is viable, we prepared alumina, titanium, and 2% titanium on alumina supported metal catalysts from the cobalt nitrate with a weight loading of 3%. Now the important thing to realize is that at this weight loading of titania, the alumina surface area, the titania contributes a titania as a dopant contributes 15.8 meters squared compared to 192 meters squared for alumina. So it contributes a very small area, right, 10 times less when it's available to the aqueous phase. The pH was adjusted to 6.5 by addition of ammonium hydroxide. Various pretreatments of the catalysts were made in order to put them in a state where we could look at their, if you will, the impact of this preparation on the temperature program reduction of each of those catalysts. And what we find is that although there is a very, very small, the majority of the area that precursor has to sit on is alumina, that TPR results clearly indicate that that a lot of the cobalt does not necessarily reside on the alumina. The solid line represents the TPR of cobalt on alumina. The dotted line is cobalt on pure titania, and the other dotted line, all right, is cobalt on the 2% titanium on alumina. Clearly, it does not resemble either alumina or titania, but tends to look more like it is on titania, which is what one would predict on the basis of the SMSE concept. So, in summary, and just to stay completely on time, the summary, I'll just focus my attention on the last coffee dot there. By adjustment of the pH of the impregnate, the solid phases of a composite oxide such as alumina or titania, will selectively exchange anionic or cationic precursors. And I'd like to thank you for your attention.
Jim, first of all, I'd like to compliment you on a very clever piece of work, and then I'd like to ask a question. This technique, I would imagine, works well as long as the two oxides have surface structures which are similar to those of the pure oxides. But you can imagine situations where you're trying to make a composite support, where you make a binary metal oxide of the surface, or you make a surface oxide layer, which is not representative of the bulk structure. And in that case, I think you can't use your mixing rules in a straightforward fashion.
Yeah.
Have you encountered situations like that?
We've played with silica and alumina, and that seems to work out all right. We play with titania and alumina, and that seems to work out all right. I think maybe we could use some of the guidelines of Israel Wax and what he sees in his Raman spectroscopy when he looks at his composite oxides to see whether or not, you were saying about essentially
Right.
they form
Right.
monolayer species
Yeah.
as opposed to individual crystallites. Those are the systems obviously you'd like to stay away from, although they might be an interesting system to look at with respect to what is the PCC of those composite oxides.
Yeah.
I'd have to say the same thing that Alex did. It's a really neat idea. One comment might be that ISS might be a really good way here to determine whether you're covering up just the titanium, for example. Look at the ISS spectra before and after absorption. But I was also wondering if during the preparation, is the preparation of the composites itself a strong absorption problem? How do you get the alcohols to stick onto the surface? Is that in itself a strong absorption problem, or what's going on there?
I guess, since none of the students here, I'm going to have to just, I'm not really sure, but as I understand it, that stuff just, you just impregnate it and it goes right onto it. It's an isopropoxide, you do it in the glove box, and you slowly hydrolyze it overnight and then you calcine it.
That wouldn't necessarily be a strong absorption problem.
No, we don't lose any, and we... Ed, can you say anything more about that? You know more of the experimental details?
Me?
Yeah.
I say something in my talk.
Yeah, he's doing another.